Welcome to the lecture 12 part A on predictive analytics, regression and classification course. We are going to discuss statistical inference of logistic regression. So in the previous lecture we have discussed the logistic regression with logit link, and then logistic regression with probit link, and then we also discussed how to do statistical inference. Now we then discussed maximum likelihood estimate of beta. How can you compute that? We discussed about the likelihood function, maximizing likelihood function, maximizing log likelihood function, and maximizing negative log likelihood function. All of them will give me the maximum likelihood estimates. One can use gradient descent algorithms to obtain the likelihood of functions. One can also show that central limit theorem can nicely kick in case of maximum likelihood estimates, that as n tends to infinity, that means if you have large enough sample size, then beta hat the sampling distribution of beta hat will behave like a normal distribution. So this is a very important result. Then as sample size is n is large, approximately it means that sampling distribution will converge to behave like a normal distribution with centering around mean and some covariance matrix omega n. N comes from this, scaling factor will take place. Now we can run statistical inference. That means if we know that what is the sampling distribution of beta hat, then we can run the statistical inference of logistic regression in the same way we did for simple linear regressions. So you don't have to implement any optimization, as you saw last times. That Python module with which implement logistic regression has two more package. One is stat models, another is sklearn, also known as scikit-learn package. The built-in function called GLM in our package named stats. You can use whatever you find suitable to your comfort zone. I'm going to motivate you with one of the very popular data set called Irish flower datasets, or Fisher's, like R.A. Fisher, who is the father of modern statistics. R.A. Fisher, he kind of collected this data in his agricultural lab. So I'm going to talk about these Irish flower datasets. There are three species of Irish. One is Setosa, another is versicolor, another is virginica. Now if you see the Setosa, and on the x-axis we put sepal length, on the y-axis we put sepal width. We see that the Setosa are sort of completely separated. Versicolor is, most point of versicolor is somewhere here, and virginica is somewhere here. So we see a reasonable overlap between virginica and versicolor. So question is identifying Setosa. Why? Because if we just have some kind of boundary, if we can create a boundary here, essentially what logistic regression will do, logistic regression will create a boundary like this. If I have to identify Setosa, then all you have to do just set up that boundary And so I'm taking the easier problem in this case, obviously, but and though I'm taking identifying setosa will be ideal easy, but I think from understanding point of view how it works will be easier if you start with the easy problem and then you move on to the difficult problem. So clearly identifying setosa will be easier than identifying versicolor or virginica. Now, given the sepal width of a flower, we want to identify if a flower is setosa. Okay, so this is the idea. So the model is like y equal to 1 if the flower is setosa with probability p, and 0 if other species with probability 1 minus p. Okay, the logistic regression with logit link model will be log p over 1 minus p equal to beta naught plus beta 1 sepal width. So I'm based on one predictor, sepal width, can I identify setosa? So that is a little difficult problem because sepal width is here, and pretty much from 2 to 4, this 4.5, pretty much 2.5 to 4.5, everything is can be either so if I just make a cutoff point like this, a lot of points also fall in the virginica, versicolor, also setosa. So it will be slightly difficult problem, but let us see. So when we fit that model, this model, I'm talking about this model, okay, when fit this model in R, so my beta naught was negative 15.71 and beta 1 was 4.78. Z value was very small or very large, p value is really small. So these coefficients are statistically significant if we assume that normality will kick in, and like we have enough data to work on. If you believe that, then what we are seeing is that as the sepal width increases, the probability that a possible flower belongs to the species setosa also increases. Now next major thing is called confusion matrix. The concept of confusion matrix is very popular in machine learning. So you do a outsample test, in the out of the sample test, and you see true is y equal to 1 means it is setosa, and y equal to 0, and predicted if it is y equal to 1 and y equal to 0. So if it is y equal to 1, if it is indeed y equal to 1 and y equal to 1, then it is correct case, or y equal to 0, y equal to 0, then it is correct case. Now these two are correct case, but the problem is these two, error 1 and error 2. So there are two kinds of error. So actually it is setosa, but model is saying it is not setosa, that is error 2, and actually it is not setosa, right? And the model is saying it is indeed setosa, so then it is a first type of error. So this sometimes in statistics language we call it true positive and true negative, and false positive and false negative. So false positive means the predict model is saying that yes, it is positive that it is setosa, but turns out that it is not setosa, so the positive is false positive. Similarly, model is saying, or your test is saying it is negative, that means it is not setosa, and so it is negative result, it is not, and then you get a false negative. So that is a false negative. So question is whether it is indeed confusion, big confusion. So I always use this cartoon of type 1 error, type 2 error, and false positive and false negative. So typically type 1 error is called false positive. Now what is it means type 1 error, false positive? So your test or your model is saying somebody that you did a test for pregnancy and test says you are pregnant, and clearly this patient is not pregnant. I don't have to tell you why he is not pregnant. Now another possible case is type 2 error or second kind of error, which is typically called false negative. In this picture you can see that a test is being given and the doctor is saying you are not pregnant. So that means, and clearly you can see that she is pregnant, so this is false negative. So your test is saying it is negative result, that means you are not pregnant, but that's a wrong result, right? So this is how I try to remember what is false positive or type 1 error and what is false negative, what is type 2 error. There are some other metrics which are very popular in machine learning called precision, recall, and F measure. Precision is a fraction of correct positive prediction. So typically it is true positive divided by true positive plus false positive, like how many positive are being predicted and how many are true positive out of the how many are predicted. And recall is true, and recall is true positive divided by true positive by false negative. So among the true cases, so how many of them are positive? So recall is the fraction of correct prediction among all true positives, and precision is fraction of correct positive prediction, how many correct positive prediction you made, and among the actual true positive how many correct prediction is made. And F measure is a harmonic mean of the precision and recall. So these are the very popular measure of how good a model is from machine learning literature. And from statistics literature, model selection with Akaike information criteria is most popular. Logistic regression with logit link will be like this, and then let P be the number of the predictors. Sorry, I should have used something different, maybe Q or K. I should use K because P I have already used for probability. So K, suppose K is the number of predictors whose corresponding coefficient needs to be estimated. Then you just calculate the L beta hat yx with the maximum value of the likelihood function of the model, and you can calculate the AIC. Once you calculate the AIC, given set of candidate models for the data preferred model with one minimum AIC is the one model that has the minimum AIC. So what is the advantage of AIC? One of the significant advantage of AIC is this measure is problem and model agnostic. Okay, for any problem, any model, you can try AIC. It means for any problem, if you can precisely write down the likelihood function, then AIC is automatic for that model. AIC is an estimator of outsample prediction error. Therefore, it represents the quality of statistical models for given set of data. So this is a very important thing. Okay, a single layer perceptron. The logit model has an equivalent formulation, which is P equal to 1 over 1 plus e to the power negative beta naught plus beta 1 x1 plus beta p xp. This functional form is commonly called single layer perceptron or single layer artificial neural network. So logistic regression is the brick which are being used to develop the neural network or deep neural network. And going forward, we will talk about it, how you can use You can think logistic regression model sort of a Lego, and you can put one Lego with another Lego and create, put lots of Lego and create a beautiful artifact out of that. So similarly, neural network, each component of a neural network can be viewed as a perceptron, single layer perceptron and model, and single layer perceptron model is nothing but a simple logistic regression. Can logistic regression have the multicollinearity issue? Yes, logistic regression can suffer from logistic multicollinearity issue. So you have to be very careful. You should check if it does have the multicollinearity issue. In such case, you have to apply ridge correction that we applied in case of simple linear regression. Unfortunately, straightforward mathematically closed-form solution for logistic regression is not available. However, Python R packages are available which implement ridge correction for logistic regression very efficiently, so you don't have to worry about those things. So implementation part, you don't have to really worry. So in practice, logit in the stats model, there is a logistic regression in scikit-learn module, logistic regression with TensorFlow module. So yeah, in GLM, in R, you have GLM in stats package, GLM net package, an efficient implementation of regularized logistic regression to handle multicollinearity is already available, so you don't have to worry about that. Now I close the lecture on logistic regression here. Thank you for your attention.